equations on solving polynomial equations. Section 5.1, the remainder and the factor theorem and synthetic division. So first, before I can discuss solving polynomial equations, let me define a polynomial. So let me define a polynomial in one variable. So a univariate polynomial. So a polynomial, let's say in the variable x, will be, well, I'll use the notation p sub n of x is equal to the sum, k equaling 0 to n, of a sub k, x to the k, where a sub k is some member in some field. Usually we'll be doing this over fields. Sometimes they won't be fields. They may just be integral domains for all k being whole numbers between 1 and n, where n here is a whole number. If a sub n is not 0, then the degree of your polynomial will be n. And I'll usually denote a polynomial as follows, saying that it's a member of whatever the field is with this little bracket of x. And so this says that I'm a polynomial in the indefinite field. Roots of your polynomial. Let A be a member of your field such that the polynomial at A is 0. Then we call A a root of your polynomial. The usual fields that we'll be considering throughout this chapter are the rationals, the reals, the complex numbers, z sub p, which are integers modulo some prime number p. We'll also sometimes be just looking at integral domains, the integers. Factoring polynomials. So if I can write f as g times h, sometimes I'll be calling my polynomials f. The reason for that is because sometimes I want to talk about a prime number, which I always denote by p. So you can't use p for more than one thing. So sometimes I'll call my polynomials f's rather than p's and q's. Okay, so f is equal to g times h, where, so I say that I can factor f into polynomials g and h if the degree of g is less than the degree of f and the degree of h is less than the degree of f. So I can factor a polynomial if I can write it as the product of two polynomials, each of which have degree less than the original polynomial. Again, the root of a polynomial is such that it's equal to 0 at that root. Another way of conceptualizing polynomials is to think of them as sequences. So for example, instead of writing 2x cubed minus 4x plus 7, I can just write down the coefficients. So 7 x to the 0 minus 4x plus no x squared plus 2x cubed plus no x to the fourth, etc. Can be thought of the sequence. The polynomial can be written as the sequence 7, negative 4, 0, 2, 0, 0. Okay. So we can think of a polynomial as just being some sequence. In which case, then you don't have, you could think of x in a polynomial as really being just sort of a figment of the notation. So it's not really there. It is just a part of the notation that we use. Of course, once we evaluate it, then we substitute a value for x. So that makes it a much more convenient sort of notation, this sort of evaluation map. Okay, so polynomials. So let me redefine polynomials. A polynomial in x. Let R be a ring, and let R squared denote the Cartesian product of R with itself. And let R to the W, where this is the whole numbers, so R to the whole numbers, equal F, such that F is a function from the whole numbers to the union of R sub I, where I is a whole number, so it's an infinite number of these, such that for every I, F at I is in R sub I, where R sub I is just R, with all but a finite number of F at I's equaling 0. So it's the sequence idea here. Then P is a member of R to the whole numbers. It's called a polynomial, and Fi is called the coefficient of Xi, just like what we had here. If R to the whole numbers satisfies the following. So now we have to say, well, you can add and multiply and things of that sort. Let P be a member of R to the whole numbers with coefficients F and G. With coefficient G. F plus G at I is just equal to F sub I plus G sub I. So these are the this is how we define these coefficient-wise. It's the ith term in this sequence. Negative F at I is just equal to negative F at I. F times G at I is just the sum, J plus K equaling I, F sub J, G sub K. Let P be in R to the whole numbers, RW, with coefficient Fi for all, I should really say, even though it sounds better this way. Okay. Even though that was precise, it just didn't sound as good. Okay. Let P with coefficient, so it's a polynomial. Let's just say, let P be a polynomial with coefficient Fi equaling 0 for I equaling, well, being a natural number without n, and let F at n equaling 1, then we denote P by xn. So meaning if everything is 0, except the nth guy is 1, then we call this x to the power n. So now, if you do that, then the definition that I gave before up here is the same. So now, using that notation. Let's look at solving first some easy equations. So first, an easy, one of the most trivial polynomial equations, a linear equation. So this is a case that n is equal to 1. This has really been solved for at least since like 5000 BC. At least, before 5000 BC, so it's older than that. So suppose P is a whole number, and I want to solve the equation x plus P equaling 0. Well, then x is equal to minus P, but minus P is not a whole number. So we must extend the idea of a solution so that we include additive inverses. So even if I wanted to solve this equation where we only had whole numbers, I'd have to extend it to the idea, well, I have to include additive inverses, so I really have to look at the integers. So if I want to solve this equation, well, I need some integers in here. Okay. If I wanted to solve the equation ax, where a is a natural number and b is a natural number, then if I let z equal x equals z minus b over a, I can rewrite this as well. Replace x by z minus b over a. Multiply a inside the parentheses, so you get az. The a's cancel, so you get a minus b. The b's cancel, so you get az equals 0. Well, and so either a is 0 or z is 0. Let's assume that a is not 0. Then z equaling 0 says that x is equal to minus b over a. But that means that we have to have multiplicative inverses. And so we must extend these natural numbers to not only include the additive inverses, but also the multiplicative inverses. And we have to include the zero factor property. And so we have to make these into an integral domain to solve a first order linear equation. And so in order to solve a first order linear equation, we must at least look at integers. Okay. So, well, not quite fields yet. We're going to study them for integral domains. Okay. Quadratic equations. So now let's look at quadratic equations, the case where n is equal to 2. So these were studied by the Chinese, the Babylonians about 2000 BC, Chinese around 2500 BC. But the most extensive collection of knowledge that we know of is from 2000 BC for solving these. So suppose I have ax squared plus bx plus c equaling 0. And let's look at them under a field, okay? Because I knew that here at least we had to, well, let's look at them at least under a integral domain. And we'll see that we'll have to extend this 4 ways. Okay, so let z equal minus b over 2a. So I'll replace x here by z minus 2a. And I'll replace x here as z minus b over 2a. So I just get z squared minus b over a z, 2's will cancel, plus b squared over 4a squared. Multiply the b inside the parentheses, so you get bz minus b squared over 2a plus c equals 0. Multiply the a inside the parentheses, so you get az squared minus bz plus b squared over 4a plus these last terms. The bz's are going to cancel. Let's get rid of all the denominators. So let's multiply everything by 4a. So we get a 4a squared, z squared, plus, well, the 4a's cancel, b squared, minus 4a divided by 2a is just 2, so minus 2b squared, plus, well, 4a times c is 4ac, equaling 0 times 4a is just 0. B squared minus 2b squared is minus 1b squared. Bring b squared minus 4ac to the other side of my equation. So by the zero factor, by the square root property, I have that 2az is equal to plus or minus the square root of b squared minus 4ac. Divide both sides of the equation by 2a. So z is equal to plus or minus the square root of b squared minus 4ac all over 2a. Plug that back in for z to get x. So x is equal to minus b over 2a plus or minus the square root of b squared minus 4ac all over 2a. Let's rewrite it as x equal minus b plus or minus the square root of b squared minus 4ac all over 2a. This is the quadratic formula. Usually we let d, the discriminant, equal b squared minus 4ac. Note that we want that d squared, that whatever here, should be in your field. But if it's not, then we have to extend our field so that this object here is in our field. So to be able to solve quadratic equations with rational coefficients, we have to extend the field of rational numbers, to include the square root of d. which is a subfield of the field of complex numbers. So, to reiterate, in order to solve a quadratic equation, we may need to extend the field to include the square root of b squared minus 4ac. And again, we usually denote b squared minus 4ac by the discriminant d. So, to solve f of x equaling 0, where f is a polynomial with rational coefficients, we will need to extend the field Q to the field extension Q of rad D, which is the set A plus B rad D, where A is rational and B is rational, if the square root of D is not rational. Similarly, to solve f of x equaling 0, where f is a polynomial with real coefficients in the indeterminate f. By the way, notice that sometimes I write f as a member of some field with the indeterminate x, and sometimes I write it as f of x as the member. You can write it either way. Usually I write it as f of x, but it doesn't really matter. We will need to extend the field to include a plus b rad d, where a is real and b is real, and the square root of d is not real. So, an example. Suppose I want to solve x squared minus 11x plus 6 equals 0. Notice that each of these coefficients are rational numbers. So I have a whole bunch of rational numbers. Well, by the quadratic formula, x is equal to negative b, so minus negative 11 gives me a positive 11, plus or minus the square root of b, negative 11 squared, minus 4a, 1, c, 6, all over 2 times a. Negative 11 squared is 121. 4 times 1 times 6 is 24. 121 minus 24 is 97. And so I have that x is equal to 11 over 7 plus or minus 1/2 times the square root of 97. And so I have a rational number plus a rational number times the square root of 97. So I have a rational number plus a rational number times the square root of something, 97. Where the square root of 97 is not rational. No, it's not. Okay, so notice we cannot solve this equation only with rational numbers, but we can solve it where I have extended the rational numbers to include the square root of 97. So it's a linear combination of rational numbers along with rational numbers times the square root of 97. Okay. Let's look at cubic equations. So the case that n is equal to 3. So this was solved by Cardano in 1539. Actually, it wasn't solved by Cardano, but he's the first person to publish it in 1539. Yeah, so, oh good, I actually see who it was. Okay, so suppose we have an equation ax cubed plus bx squared plus cx plus d equaling 0, where a are some members of some field and a is not 0. So this was partially solved by Omar Khayyam in 1079, and it was fully solved by Niccolo Fontana in 1535. He's usually called Tartaglia, and the reason he's called that is because he was in a duel and he lost most of his tongue in a duel, and because of that, this I guess in Italian means he stammers, he stutters, and so he's called the stutterer. Tartigliano is the name we usually call him, but actually that's kind of a mean name. But that's usually what they call him. In 1535, in 1539, it was first published by Cardano, and he actually asked Tartaglia to how he saw the cubic. So Cardano said, "Well, if you tell it to me, I won't." Well, after 4 years, he actually published it. So they were quite angry at each other. Fontana was not very, and he said that he would never divulge, but he did. But it's now called Cardano's formula, just because he published it first. So first, let's try to depress this equation. Let's try to look at a simpler equation, similar to what we did above. So let x equal z minus b over 3a. Notice here, I did for linear z minus b over 1a, quadratics z minus b over 2a, cubics z minus b over 3a. And this so to get rid of the term of power 1 less than a leading order term, you just do z minus b over na, where n is the degree of your polynomial. Okay, so replace x by z minus b over 3a, x by z minus b over 3a, x by z minus b over 3a. Cube, using the special product formula, a minus b cubed is a cubed minus 3a squared b plus 3ab squared minus b cubed. Okay. Special product formula for a minus b squared, a squared minus b minus ab plus b squared. Multiply a inside the parentheses, so you get az cubed. The 3's and the a's cancel, so you get bz squared. One of the 3a's cancel, so you get b squared over 3a, z. One of the a's cancel, so you get b cubed over 3 cubed is 27a squared. Bz squared minus 2b squared over 3az plus b cubed over 9a squared, then plus cz minus bc over 3a plus d equals 0. The b z squares cancel. Collecting all the terms, there's a whole bunch of things involving z, no z squares, all z. And so let's rewrite this as z cubed plus something times z, I'll call it p, plus something else, I'll call it q, equals 0. So rather than starting out with, oh, and then did I, oh yeah, I divided everything by a here, going from here to here. So now I can, instead of looking at ax cubed plus b x squared plus cx plus d equaling 0, I can now just look at z cubed plus pz plus q equals 0. A simpler equation. So now it's a monic equation, and it doesn't have the term that's one less than the degree of your polynomial. So z cubed plus pz is minus q, just bringing the q to the other side of my equation. Let z equal, so now let's try to solve this. And let's derive the formula to solve this. So let z equal u plus v z by u plus v. And so again, by the special product formula, it's just u cubed plus 3u squared v plus 3uv squared plus u cubed, so it's v cubed. Let's collect the v cubes and u cubes. And then this is plus uv times u plus v. So I have a u plus v in common. So I have here u cubed plus v cubed plus the product of these two equals minus q. Well, if I make this term 0, then I have that I just have to solve this quantity. So let's make this guy 0. So I have that, well, let's solve for v, subtract p from both sides, divide by 3u. So v is equal to minus p over 3u. If I assume that v is minus p over 3u, then I get, substituting for v, minus p over 3 cubed, a u cubed minus p cubed over 27u cubed equals negative q. Multiply both sides of my equation by 27u cubed. So now I get 27u to the 6th plus 27 q u cubed minus p cubed equals 0. But now this is quadratic and u cubed. So I can solve this because I know the quadratic formula. So I can use the quadratic formula to determine u cubed. I can pick one of the solutions to this because your quadratic formula gives you 2 solutions. Just pick one of them, doesn't matter. So I know what u cubed is. So I can figure out what u is by taking the cube root. So pick one of the cube roots to find u. Once I know u, I know what v is. Therefore, I know what z is. But if I know z, then I know what x is. So I know one of my x's. I can then use this root to solve the reduced equation, which will be quadratic. And so we're done because we know how to solve quadratics. So therefore, we've determined that there is a formula to solve any cubic involving cubic roots, square roots, along with algebraic operations of addition, subtraction, multiplication, division, powers. So this is some algebraic function of the coefficients. Okay. Let's look at the quartic. Why is it quintic? The quartic equation. The quartic equation. So n equal 4. Again, this is Cardano's formula in 1545. He was, again, he's published, first published it. Cardano was really not a mathematician. He was an investor, and he actually invested in formulas. So he would purchase formulas and publish them, or steal formulas and publish them. So the actual person who did this was Ferrari in 1540, and I guess Ferrari actually sold the formula to Cardano. So it was semi-legitimate. Again, this is Cardano's formula because he published it, but it's done by Ferrari. So all these Cardano formulas are not done by Cardano, but known by his name. So suppose I have ax to the 4th plus bx cubed plus cx squared plus dx plus e equaling 0. And suppose that a is not equal to 0. Then, just like above, I'm not going to probably show it. You can let x equal z minus b over 4a, and you can use this to eliminate the x cubed terms. You can also divide this polynomial by a to obtain a monic polynomial. So doing the above stuff, you get an equation of the form x to the 4th plus px squared plus qx plus r equals 0. Assume that you can factor this. Oh, by the way, sometimes this is called the biquadratic. So assume you can factor this into x squared plus t times x squared plus ux plus v. And we got to figure out what x, s, t, u, and v are. So let's multiply these out and set coefficients equal to each other. So multiplying this, I get x to the 4th plus s plus u x cubed v plus su plus t all times x squared. And then let's do the x term. Oh, u, well, let's do this one. S v plus t u tv. So now the x cubed term must be 0. So s plus u must be 0. The x squared term is p, so v plus su plus t must equal p. In the x term, sv plus tu must equal q. And lastly, the tv must equal r. So equating coefficients give you these. So from this, I get that s is equal to minus u, just subtracting u from both sides. Subtracting, letting s equal minus u, I get that this is minus u squared. So let's bring this to the other side. So I get v plus t is p plus u squared. And q is just tu plus sv, but s is a minus u, so minus uv. Okay, so square both sides of this. So I get that p plus u squared squared is v plus t squared. So let's use the special product formula. So that's v squared plus 2vt plus t squared. Let's square this. So I get q squared is t u minus uv squared. I can factor out a u. So that's really u squared times t minus v quantity squared. And so I get, well, t squared minus, again, using the special product formula, minus t v plus v squared. Okay. So I get, oh, I guess let's write the other direction. So u squared v squared minus 2 u squared vt minus plus u squared v squared. Okay. And so I get that. Multiplying this by u squared, I get 1 second. I get oh, I'm sorry. Okay, so if you bring that to this side, okay, so if you bring this to this side, so that's equal to this. So I get u squared, p plus u squared squared, minus this q squared. Okay. Will just equal. So if you just multiply this guy here, yeah, let's just write this. P plus u squared squared. And then this is q squared. Okay, so I should have written one more line, I guess, then. So this, multiply this by u squared. So this is u squared p squared equals u squared plus 2u squared v t plus u squared t squared. Okay, so if you take this term here and subtract this term, you get u squared p plus u squared squared minus q squared. Oops, I wrote it, but I didn't write it. Okay, so u squared v squared. So these cancel. You get 2 of these minus a negative 2, so that's plus 2 of these, so you get 4 of these. U squared v t's. The u squared t squares cancel. Okay. And tv is just r. So you get that this is equal to 4ru squared. Let's square this out. So I get u to the 4th, again by the special product formula, plus 2 p u squared plus p squared. And this is all times your u squared. Minus q squared equals this 4ru squared. And so I get u to the 6th plus 2p u to the 4th plus u squared times p squared minus the 4ru squared. So let's bring this over. Minus q squared equals 0. But this is cubic in u squared. So this is u squared cubed. This is u squared squared. This is u squared. So I can solve a cubic by what we did above. So I know u squared. But I know u because I know I can take the square root. And so I know what u is. But since I know what u is, then u, I know s. And since I know s, then I know that what t plus v is and t minus v. So that means I know what t is. And what t is, I know what v is. And so you then solve both of these quadratics. And so you can, from here, you can take one of the solutions and you know what x is. And so that means that now you know the formula for this quartic equation. Well, you know one of the solutions, you can, which is then reduced equation would then just be a cubic, and you can solve that by the above. So you know what, you know a formula in the coefficients. It's a complicated formula, but at least there is some formula. Coefficients of the polynomial is some sort of algebraic function of those coefficients of the polynomial. Degree 5 and above actually have no algebraic formula in terms of the coefficients. They have other formulas, but not algebraic formulas. They're more complicated. For the 5th degree, you can actually, if you include one solution of a particular 5th degree polynomial, then you can write it as an algebraic function of the coefficients plus that one solution of a 5th degree polynomial. It turns out that, well, the impossibility of finding a algebraic formula for polynomials of degree 5 or above was discovered by Ruffini in 1799 and by Abel in 1824. It was not quite, it was hinted at by Lagrange in 1770 and by Gauss in 1798. It was further refined by Galois in 1830. He actually gave a technique that determines which polynomials can be solved in as an algebraic function of their coefficients and which cannot. So this was done when he was young, I think 15 or 16 years old, Galois. He was actually killed in a duel, I think, when he was 19 years old. Similarly, Abel solved this when he was quite young also. He was like 21. He died of tuberculosis when I think it was like 27. So some of these guys were young when they did this. So in general, to solve polynomial equations, it's best not to use formulas because either the formulas are so complicated as to be almost useless, or there are no formulas. So, example. Let's see, what time is it? 3 minutes. Let's just look. Okay, so I think I'll end it here because I have a few minutes, but I don't think I have enough time to actually solve this equation in 3 minutes. Okay, so I think that's it for today. So I'm going to end that for today.
Professor, I have a
Yes,
question.
questions.
You said our grade that we see on Canvas is
It may not be really very good to use these type of formulas to solve these equations. Okay, so let's do this. So let me just tell you. Suppose I want to solve x plus 8x squared minus 106x minus 105 equaling 0. So the first thing to do is to get rid of the cubic term. So you would just do x equaling z minus, well, I have here a divided by 4 times 1. So 10 divided by 4 is, well, 5/2. So let x equal z minus 5/2. If you do that, then you'll get something of the form z minus 59 over 2 z squared minus 21z plus 1,485 over 16 equals 0. Okay. I'm just showing the major steps in this because even showing the major steps will hopefully convince you is really probably not the first one you should try, which is sort of to plug it into a formula, or at least actually the actual general formula is very long, so we'd have to go through these intermediate steps before even plugging it in. Okay, so now suppose that I could factor the z to the fourth into z squared plus sz plus t times z squared plus uz plus v. So if I do that and I equate coefficients, then I can find a equation in u. So I get u to the sixth minus 59 u to the fourth plus 499 u squared minus 441 is equal to 0. So I see that this will be cubic in u squared. So if I let u equaling of w equaling u squared, I get u cubed minus 59 u squared, w cubed minus 59 w 99 w minus 441 equals 0. Again, let's try to get rid of this w squared term. And so you just do w equaling y minus over 1 times 3. So 59 over 3. The minuses cancel. So you would plug that in, simplify. You get something of the form y cubed minus 1,984 over 3, y minus 157,696 over 27 equals 0. To solve this, well, let y equal m plus this guy, 1,984 over 3 divided by 3m. So that'll be over 9m. Plug that in. You get m cubed plus 780953190 cubed minus 157,696 over 27 equals 0. Let n equal m cubed and multiply both sides of your equation by n by 729m. You then get 729n squared minus 4257792n plus 780953190 equals 0. It's quadratic, so you can solve it. You can plug that into your quadratic formula. And so you get n equals, I simplified it a little bit, 512 over 27 times the quantity, 154 plus or minus 45i rad 3. Well, I'll choose the plus sign. And then to figure out what m is, well, you have to take the cube root. I'll take the regular cube root. And so I'll choose the just the regular cube root of this. So I get cube root of 512 is 8. Cube root 27 is 3 over the cube root 54 plus 45i rad 3. And so you get, well, once you know m, what y is, just plug in m here. So you get m plus the, what was it, 1894 over 9 m. You can do a little bit of cancellation here. Simplify this with a lot of work. You get that this is 88 over 3. So even though it's got like cube roots and square roots and i's in it and all that, by a lot of manipulation, you get that it's 88 over 3, which makes actually, then you can figure out what your w is by plugging in you get 49. Then you figure out what u is by taking the square root. So it's plus or minus 7. I guess I'll put the plus sign. Then you can just plug in and figure out what v is. And so then z is equal to, well, negative 5 halves or negative 9 halves. And then from there, you figure out what x is. Well, you can use either of these two, but since they're both nice, you can reduce your equation to get, so divide by x plus 5 and x plus 7 to get this reduced equation. And then you can solve it. And so then you get x is negative 7, negative 5, negative 3, and 1. Okay, so, I guess I'll just sort of do that. Or, so you solved it, but maybe that's not the easiest route. To give you a hint that maybe there are easier routes to go, let's redo this a different way. And so maybe not trying to do something involving a general formula is not the best route to go to solve these problems. In the future, oh boy, I will give you algorithms. Okay. I'll give you algorithms that will try to solve these equations. So I'll give you algorithms that are applicable in many situations to be able to solve these equations. And they'll be applicable for problems that I give you. And then give you a hint at other ways of doing things. Okay, so let's do this. So I have x to the 4th plus 10x cubed plus 8x squared minus 106x minus 105 equals 0. Now, if you notice the following, I have here some even and some odd powers. If I add up the odd numbers, the odd powers, so let's just add up the coefficients of that. So that's 10 minus 106, which is 96, negative 96. Let's add up the even ones. 1 plus 8 is 9, minus 105, 96, negative 96. Those are equal. So what that means is I have a factor of x plus 1. So I should try to rewrite these so I can factor out the x plus 1. And that's what I'm going to do. So now I just noticed that this, I should be able to factor relatively easily. So rather than going through all this sort of stuff before, where we had to simplify, like things involving cube roots of i's with square and dealing with horrible numbers. Well, let me try to write 10 as something involving 1 and 9. It's something else. So x to the 4th plus x cubed plus 9x squared plus 9x cubed. So this is a 9. So I want to write this 8 is 9 plus something. So 9x squared minus x squared. So this is a minus 1. So I'll try to write this. Next guy is a minus 1. So minus x. Well, to get minus 106, I'll do a minus 105. And then, well, minus 105x minus 105. So now let's group these first. Let's group each pair. So the x to the 4th plus x cubed, I'll group that. 9x cubed plus 9x squared, I'll group that. The x squared minus x squared minus x, let me factor out a negative and group these. So if I do that, I'll get a minus in front of the x squared plus x. Again, I have a minus here, so let's factor out the minus. So these will both become plus. And I have a 105x plus 105 equals 0. Let's factor out what I can. So from this first grouping, let's factor out x cubed. What remains is x plus 1. From the second grouping, let's factor out 9x squared. What remains is, again, x plus 1. From this next grouping, let's factor out x. What remains is x plus 1. From this last grouping, let's factor out 105. What remains is x plus 1. Therefore, x plus 1 is in common with every term. What remains is x cubed plus 9x squared minus x minus 105. So now let's look at this guy. So if I look at this guy, well, let's try to rewrite this as follows. As a minus 3x squared plus 12x squared. So I'll give you, I have to have negative 3 times 12 is negative 36x. And then I need to get minus x, so I have to do plus 35x minus the 105. So now let's factor out what's in common here. X squared, what remains is x minus 3. Factor out what's in common here. 12x, what remains is x minus 3. Factor out what's in common here. 35, what remains is x minus 3. So now factor what's in common, x minus 3. What remains is x squared plus 12x plus 35. It's quadratic, monic, so I should be able to factor that. So this is just going to be an x here. Drop down the plus, times plus gives me a plus. I want two natural numbers, or two whole numbers, whose product is 35 and whose sum is 12. So 7 and 5. Put the larger factor first. The factor with larger absolute value first. And so I have here x plus 3 times x minus 3 times x plus 7 times x plus 5 is 0. So now I can use the zero factor property, the fact that this is a polynomial over integral domain. This polynomial is an integral domain. Therefore, if the product is 0, then each factor, then at least one of the factors is 0. So either x plus 1 is 0, or x minus 3 is 0, or x plus 7 is 0, or x plus 5 is 0. So either x is negative 1, positive 3, negative 7, or negative 5. And notice we get the same result that we got, but with a lot less work. In the future, I will give you an algorithm to do this, and it will actually not involve factoring, but the sort of the technique that I gave you before, where it will involve synthetic division, and somehow knowing what possible things to look at. Okay, so before I continue, let me give you a definition. First, of a ring. So let's say that a ring R is a set along with some operations. I'll call it plus, which is an operation from the Cartesian product of the set R cross R to the set R, and multiplication, which again will be a Cartesian product, a function from the Cartesian product of R with itself to R, that satisfy the following. Well, it's what I said. It's in the defining the Cartesian product. If A is in the set R and if B is in the set R, then A plus B is also in the set R. Next, so that's the closure property for addition. Next, the associative property for addition. A plus B added to C is the same as A added to B plus C. Next, the commutative property of addition. A plus B is equal to B plus A. In general, if we have a operator on some set, the one that commutes is always denoted by plus. If something else happens, like it doesn't commute, then we use multiplication for the other one. Next, there is a nullary operator on the set R such that, well, there exists a quantity, so this is the existence of a additive identity, the additive unit, the existence of 0. There exists a number denoted by 0 in the set R such that for every element of my set R, every element A of my set R, A plus the additive identity is equal to the original number A. And so I have that this number, this quantity 0, is a right additive identity by commutativity above. We also have that it is a left additive identity. The additive identity 0 plus any quantity A is equal to the same quantity A. There exists an additive inverse. So there is some unary operator, minus, such that for every element A in my set R, there exists an element denoted by minus A in the set R, such that A plus the additive inverse of A is equal to the additive identity. Another way of stating this is that I can always solve the equation A equals 0. This is also, besides being it's also a left additive inverse by commutativity. So really, this is a statement about solvability. So x plus a equaling 0 has a solution. Okay. Next, we have also the closure property for multiplication. So if A is in the set R and B is in the set R, then A times B is in the set R. We have the associative property for multiplication. A times B times the quantity C is the same as A times the quantity B times C. We also have that multiplication distributes over addition. A times the quantity B plus C is the same as A times B plus A times C. Okay, so those constitute what is called a ring. Polynomials are rings. Now, in addition, we will say that it is a commutative ring if, in addition, it satisfies A times B equaling B times A. That multiplication commutes. And so if multiplication commutes, we call it a commutative ring. If there is a multiplicative identity, then we say that this is a ring with identity. Okay. Now, it may not be commutative. So if it satisfies 1 through 8 and 10, so if it's a ring and there exists an identity, it's called a ring with identity. If it commutes, then it would be a commutative ring with identity. So we have a nullary operator stating the following. There exists an element denoted by 1 in the set R, such that for every element A in the set R, the multiplicative identity times A is just equal to A. So this is a left multiplicative identity. And A times the multiplicative identity is equal to A for every element A. So it's also a right multiplicative identity. We wouldn't know that. We have to have both of these because we don't necessarily know that it commutes. Multiplication commutes. Now, an integral domain. Basically, integral domain is things that like integers. So integral integers, think of. So if it satisfies all these up to step 11, it'll be called the integral domain. First, assume that 1 is not equal to 0. So suppose that the multiplicative identity and the additive identity are not the same. If they are the same, then unfortunately, you'll just get a ring with one element. So basically I'm saying suppose that I have a ring that has more than one element in it. If A times B equals 0, then A is equal to 0 or B is equal to 0. And so this is the zero factor property. So if the zero factor property holds, then we call it an integral domain. So if you have some ring with commutative ring with identity that also satisfies the zero factor property, we call it integral domain. And lastly, well, let's recall the division algorithm. So the division algorithm says that if you have two numbers, let's say 8 and 5, then you can divide them. And so you would get some dividend divided by divisor is equal to a quotient plus the remainder for the divisor, supposing that the remainder is less than the divisor. Or I can say that the dividend is equal to the product of the quotient times the divisor plus the remainder. Let's do the same thing here. Let P, in the future, I may sometimes, instead of writing P for a polynomial, write F as a polynomial. I'll do that when things involve prime numbers, because I always use P for prime numbers. So if I'm going to involve something involving a prime number, all polynomials won't be called P, they'll be called F. So let P be a polynomial with coefficients in some field with some indeterminate x. Let D of x be in the same polynomial field. So be a polynomial with coefficients in the field f. Suppose D is not 0, then there exists a unique polynomial Q of x and a polynomial R of x such that the dividend, P of x, just like before, is equal to the quotient, Q of x, times the divisor, D of x, plus a remainder, R of x, where, well, instead of these, somehow these have got to be smaller. The remainder has to be smaller than the divisor, where the degree of the remainder is less than the degree of the divisor. So it's the same thing we had with integers. Polynomial, more or less polynomials can be integers. So a lot of the properties that work for integers work for polynomials. The remainder theorem. Okay. A ring. Let P of x be a polynomial in x. Then the remainder of P of x divided by x minus a is just P of a. So, in other words, this means that there exists some quotient, Q of x, polynomial, such that P of x is equal to x minus a times Q of x plus P of a. And we can just see this from the remainder theorem. If I let D of x equal x minus a, then the remainder has to be a polynomial of degree less than x minus a. Well, the degree of x minus a is 1. So it has to be a polynomial of degree less than 1. There's only one the only polynomials of degree less than 1 are polynomials of degree 0, meaning constants. And so I have to have that P of x is constant. But if you plug in x equal a here, to this first term, you'll just get 0. And so P of a must be the constant. And so it's just P of a. And so the remainder of P of x divided by x minus a is indeed P of a. So to figure out, to evaluate a polynomial at some point, that's the same as just dividing the polynomial by x minus a and figuring out the remainder. And so that's why it's called the remainder theorem. And of course, if the remainder of this quotient, P of x divided by x minus a, is 0, then that means that x minus a is a factor of the polynomial. So let's do some examples. On page 508, let me do, there it is. On page 508, let me do the following. So find each value by substituting the given value of x into the polynomial and simplifying. Then find the value by performing long division and finding the remainder. So let me do that. So problem number 12. Let's first evaluate p at -2. So I'm going to substitute for x -2 and then evaluate that. And so I have here 5. Okay. I have here 5 times -2 cubed plus 4 times -2 squared plus -2 minus 1. And so p evaluated at -2 is just 5 times -8, -40, plus 4 times 4, 16, minus 2 minus 1. And so p at -2 is -3, that would be 13, -27. Now let's check the remainder theorem. So it says, well, I want to divide. And so let's do a division. And let's do it by, oh, they said long division. Let's do it by long division. I didn't want to do long division, but I have to, I guess. So let's divide 5x cubed plus 4x squared plus x minus 1. Let's divide this by x plus 2 and check to see what the remainder is. Hope I have enough room. Let me insert a new page so they have enough room. Maybe what I'll do is, actually, let me move it down. Okay. I'll do the division, the long division, and then in that space that I've missed, I guess I'll do synthetic division. Okay, so now I'll do the remainder theorem. Okay, so I'll do it using the remainder theorem. So let me show it first using synthetic division, and then using long division because they told me to use long division. So it'd be 5x cubed plus 4x squared plus 1x minus 1. Drop down to 5 times -2 is -10 plus 4 is -6 times 2 is 8 plus 1 is 9 times -2 is, let me just check, 5x cubed, 4x squared, 1x minus 1. Okay, let me just check something, because -18, that's -19. Let's see which one. Let me just check something for 1 second. 5x cubed plus 4x squared plus x minus 1. And let's plug in, was it -2?
Professor, I think you multiplied wrong for the bottom part, the remainder theorem.
Oh, 12. Thank you. 12. Yeah. So that, yes, I did write something wrong there. Okay, so this is in it. Huh. Okay. 5, 4. Ah, okay. Okay, so let me just check something. Okay, so negative 27 is correct. Okay, so positive 12. Thank you. Positive 12. There it is. That gives me 13. That gives me minus 26, minus 27. Okay, there, thank you. Yes. Okay, so that says by the remainder theorem, P at negative 2 equals negative 27. Let's do long division. So 5x cubed divided by x is 5x squared. And so if I multiply it, I get 5x cubed plus 10x squared. And I subtract. And so 4x squared minus 10x, the 5x cubes cancel. 4x squared minus 10x squared is a minus 6x squared. Drop down the x. Negative 6x squared divided by x is negative 6x. So I get a negative 6x squared minus 12x. I subtract. The negative 6x squares cancel. And so I get x minus a negative 12x, same as x plus 12x, which is 13x, minus 1. Good. 13, x divided by x is 13. Let's multiply by 13. So I get 13x plus 26. I subtract. Minus 1 minus 26 is minus 27. And so, by the remainder theorem, I have that P at negative 2 is negative 27. And that is good because now all the answers are the same. And so you could plug in negative 2 and just see that it works. Or you can use synthetic division, which is faster, usually with less errors, even though I did 2 times 6 and I got 9 or something. Usually with less errors, or you could do long division. And you get your answer. Use the remainder theorem to find the remainder that occurs when P of x equaling 3x cubed, 3x to the fourth plus 5x cubed minus 4x squared minus 2x plus 1 is divided by each binomial. Use a calculator on exercises 21 through 24. So let's do this. I wonder if I can actually do this. So let's do synthetic division. So I'll divide by x minus 2, 3x to the 4, 5x cubed minus 4x squared minus 2x plus 1. Okay, 4, 3, 2, 1, 0. Okay, good. So drop down to 3 times 2 is 6 plus 5 is 11 times 2 is 22 minus 4 is 18, times 2 is 36, minus 2 is 34, times 2 is 68, plus 1 is 69. And so this says that the remainder is 69. Maybe I'll, oh, this will, so I don't know, I'll have to, so the remainder is 69. And that is your answer. Okay. Field extensions. So let the field F and the field fancy F be such that the set F is a subset of the set fancy F. F is a field, and fancy curly F is also a field. Then we call curly F an extension of F. So if you have a field that's bigger than another field, then we say that it's an extension of the other field. A minimal polynomial. Let A be in a field F with curly F here, being a field extension of F. The minimal polynomial for A is f of x, a polynomial in F, such that f of x is an irreducible monic polynomial in F, and f of A is 0. In other words, F is a monic polynomial of least degree having A as its root. Actually sounds better, its root. Even though it's not the only root, but at least I don't have two A's there. Okay, find the minimal polynomial for 2 and 3 in Q. Oh, okay, so actually I just did it here. So if 2 is a root, then one possible, well, then a factor of the polynomial would be x minus 2. If 3 is a root of the polynomial, then x minus 3 is a factor of the polynomial. If I multiply those together, I get x squared minus 5x plus 6. Both 2 and 3 are roots of this polynomial, and there's no other polynomial of less degree. Obviously, if you get rid of one of these, you're not going to have either 2 or 3 as being a root. And so the factor theorem. Let A be some member of a field F. This is a root of P of x, a polynomial with coefficients in F. If and only if x minus A is a factor of the polynomial P. And we could see that by the division algorithm, or even the remainder theorem. So the only way that this can be a root, if this is 0, well, if this is 0, then this is a root, because this is a factor, x minus A is a factor. If x minus A is a factor, that means this is 0, and so that means that A is a root. And so we have the there. Okay, thank you, move. So we have the factor theorem. Oh, and I actually say, so the proof is, well, P of A is 0 if and only if P of X is equal to X minus A times Q. This is what I showed above. '27. Use the factor theorem to determine whether each statement is true. If the statement is not true, so indicate. So I want to show that X minus 1 is a factor of the polynomial P of X equaling 3X to the 5th plus 4X squared minus 7. So I can just look to see if the remainder is 0. And so let's do that. So is this a factor? Well, this is a factor if and only if it is a root of the polynomial. A root of the polynomial means that this is 0. And so let's check if this is 0. Three times 1 is 3. 4 times 1 is 4. And so it's equal to 0. So therefore, by the factor theorem, it is well, this is since this 1 is a root, then by the factor theorem, X minus 1 is a factor. So yes, this is a true statement. '53. Let P of X equal 5X cubed plus 2X squared minus X plus 1. Use synthetic division to find the value. So I want to figure out P at I, but I don't want to plug in like what I just did here. Rather, I want to, so I guess maybe I should say, what I said in words. So rather than actually plug in, I want to use the fact that it's a root. And so what I'll do is I'll just use synthetic division. And so I have I 5X cubed plus 2X squared minus X plus 1. Let me drop down the 5. Actually, let's get more room here. 2 minus 1, 1. So let me just get more room. 5, drop down, times I is 5I. 2 plus 5I. Can't combine them. Now, let's multiply I times 2 plus 5I. So I times I becomes I squared is a negative 5 plus, well, 2 times I is 2I. Now let's combine. I can add real parts and just attach the imaginary part to it. So negative 1 minus 5 is negative 6, 2I. Okay, Now, let's multiply. And so I times I is -1 times 2 is minus 6i. 6 times I is 6i. -1 minus 6i. And so I have that P at I is a -1 minus 6i. And that's your answer. So notice, actually, in this case, it might even be almost easier. Maybe, maybe not. Actually, it's just an I, so it might be easier just to plug in. But they're almost the same amount of difficulty in this case. A partial solution set is given for each polynomial equation. Find a complete solution set. So this is giving you practice for the technique, the algorithm that we will be giving to you later today. And so if you have a solution, how do you then solve the equation given this fact? So if you're able to get some solutions, maybe you can make the problem easier. And so let's do this. And I'll probably do it this way. And so I have here a half is my root. And I'm doing 2x cubed minus 3x squared minus 11x plus 6. Drop down to 2. Times a half is 1. Minus 3 is minus 2. Times a half is minus 1. Times minus 11 is minus 12. Times a half is minus 6. Plus 6 is 0. And so I have that 2x cubed minus 3x squared minus 11x plus 6 by the factor theorem is just equal to x minus 1/2 times 2x squared minus 2x minus 12. So this says that this product is 0. Actually, let me multiply let's take the 2 over to the other term so that it looks easier. So I'll divide each of these coefficients by 2. So I get 2x minus 1 times minus 6 is 0. Okay. And so I can actually factor this monic quadratic trinomial as follows. Well, this is just x I have a minus, and so I'll drop down the minus. Minus times minus times minus is plus. I want two whole numbers whose product is 6 and whose difference is 1, 3 and 2, and put the root with larger, set each factor equal to 0 by the zero factor property, by the fact that this is an integral domain, that a polynomial with integral domain coefficients factored to 0. Again, by that zero factor property, the fact that this polynomial is an integral domain. The polynomials of this type form an integral domain. Add 1, divide by 2, add 3, subtract 2. So therefore, the roots of this polynomial are 1/2, 3, -2. And so I have found all the, in this case, notice that this is a cubic equation, and I have found all 3 roots to this cubic equation. And so